So we're going to talk about our new topic starting today. Um, and specifically, we're going to discuss files and file systems, or if you prefer, the file system from the viewpoint of the operating system. So first off, what's a file? Well, you'll recall that in the von Neumann architecture, literally everything is bits. Okay, so you've got operations which are represented by opcodes. You have the instructions themselves, right, which contain the opcodes. So instructions with registers, all of that, all of that gets represented as binary data. And so, also represented as binary data are all data that you want to use. The results, the input, the temporary values that you make use of, it's all binary. Everything at the heart of the digital computer in modern times, all of which make use of what we call von Neumann's architecture. All of that, the data and the instructions or the code are all binary. Okay. Now, the abstraction that we make for the user, okay, of the computer is that we are able to group data points together, okay, into abstractions that are called files. Okay. You have this is such a fundamental understanding of information that you probably began, right, by thinking that computers were made up of files. Okay, your first days using computers had you clicking on files to open them up, all right, or opening files or seeing files inside some kind of application that looks something like this, right, where it tells you where on the computer the file is, and you can drill down and find these abstract and discrete components, okay, called files. And we keep up with things like the date modified, the date that it began, although you can't see that here, its type, and we'll talk about all of these things, including its name, and then this dot here with the some number, usually three, but sometimes fewer, and in this case, dot save, for instance. Uh, Extension called the file extension. We'll talk about what all that really means and what it looks like and means to the operating system as we go through this. So users need to store persistent information over an extended period of time, and they conceptualize the data that they are making use of so that it's meaningfully organized and compartmentalized into files, right? That data needs to be stored on media, okay? So files actually need to be stored for persistent later use on some form of media, okay? Uh, Typically, you'll be thinking of a hard drive, okay? Or a USB device, okay? Or some other, we used to call it flash memory. I guess that's still technically what it's called, flash memory, okay? Or perhaps on a floppy disk. Oh, we're going back to the old days, right? Or, hey, better yet, perhaps on a CD, okay, or a DVD. These are all examples of media where we intend to store the files. But, and this is a song that's kind of old hat to us now, the way that these work is ugly slash complicated. Okay, and so what we want to do is we want to provide a structure. Okay, if we the operating system want to provide a structure and an abstraction that helps the user not have to worry about the implementation details of how that actually works. Okay. So we're going to try to abstract all that ugliness away, at least from the viewpoint of the user, and to some degree, as much as possible, from the viewpoint of the operating system designer, right? And just think about this on the bit level. Okay. Now, obviously, we know that drivers are in place. Drivers are in place to help us abstract out those nitty-gritty, dirty details. And we'll just assume at the level that we're going to be working at today, we'll assume that those drivers are good to go. Okay, that they take care of all that interfacing that needs to happen between the operating system and whatever manufacturer of whatever hard drive we actually have, or whatever USB device in the manufacturer's wrinkles, and whatever CD and DVD we use, right? Whatever hardware we use, whatever manufacturer came up with whatever set of instructions they require, right? A lot of this is standard, but some of it is not, right? And so the drivers take care of that. But we want to build an abstraction that is useful for thinking about files and file systems, and for providing a layer of usefulness to the user. Okay. So a file then, and this is the formal definition from the book, is a named collection of information managed on secondary storage by the file system. The files can be viewed as a single abstract unit of data storage, okay? And can be accessed / viewed or modified using high-level operations provided by the file system without knowing the specific characteristics of the underlying storage data, okay? So generally, and this is not true in any way, but generally from the user viewpoint, okay, the file can be considered as sort of the fundamental unit of data storage and data access. That's not true, right? The fundamental unit of data storage and data access is the bit. But we don't need our users to know about bits necessarily, okay? We don't enforce that they have that knowledge. Maybe that was a mistake, you know? I'm open to the debate that says that we should have never created these computers that were so powerful that could be used by people who to give power to people who don't understand how the computers work, right? Because people who do understand how the computers work can sneakily take control, right? Or limit the power of some people. I'm open to that just as a philosophical debate, but it's not the debate that we're going to have in the class today, okay? Was black box design a good idea? I don't know, okay? But we're going to take all that discussion, we'll put it off to another day in another place. Black box design exists, okay? The file is not a real thing, right? But from the user's viewpoint, it's the fundamental unit of data storage, okay? So you can let the implications of that sink in. From the user's viewpoint, it is very much a real thing. Of course, we know that it's just a collection of bits, a collection of individually accessible data, right? It's an abstract unit of data storage. The operations on that data, right? Accessing the data, viewing the data, modifying the data, are all provided by the operating system through something called the file system. Okay, file system. All right, so it is the portion of the OS whose job is to implement the concept of files. I'll write that down. component of the OS, if you like, whose job is to implement the file abstraction. And we can add to that not only just the notion of a file, but the notion of a file is not useful unless we have operations that can be used on those files. And all operations performed on files. Okay? That's what the file system is. Now, a quick aside here about the structure, let's say the fundamental structure of files. Because the notion of a file is not a real thing, but is really just an abstraction of data, the operating system designer has several options, and this is only the two most popular ones, has several options for how to conceptualize and how to encompass what a file is, right? A file could be just a stream of bits, okay? Or a file could be a collection of records. And we're not gonna dive into the nitty-gritty details about that too much. This is probably the more popular approach. This is the older approach. So we're gonna focus on this one pretty much exclusively today, but it does bear pointing out that you don't have to do it this way. That's just the most popular way that we're doing it in modern operating systems. Okay. Yeah, there are advantages to records. Files are so fundamental that you will often hear people say on Unix and Linux systems that everything is a file. Okay. So it's not only a useful abstraction for the users of operating systems, but it's actually a useful abstraction when thinking about designing operating systems as well. Okay. So what that means in everything is a file, right, is the notion that there are no devices. Okay. All devices can be treated as files. So like in Linux, for instance, if you want to write out to a device, you are writing out to a specific file, right? You're writing bit data out to a specific file, right? So that really fundamentally maps to what an operating system can do, right? The abstraction that an operating system provides, not only for the user, but also for the programmer or the designer themselves. So since we're going to focus on records, it's worthwhile to say what a record is. It is a structure of related data items. Sometimes those data items are of different data types, but they're identified within a file by a record number or a unique key field. If we have files, then we need to be able to access those files. Okay. And there are two ways that we go about as an operating system for providing the interface to access files, right? They are sequential access Sorry for the terrible handwriting. And direct access. That the tablet's being particularly ornery today, so if I scribble down something that you can't understand, don't hesitate to ask. Sequential access is what it sounds like. Direct access is where the ability to directly access specific records is provided. Okay. This one is actually the most common technique. Okay. Because it turns out that that the easiest abstraction for a file, right, is that it contains records, but that we access those file components by beginning at the beginning of the file and reading down to where we want to go, okay, until we reach the position where we want to access. And there's a lot of overhead for maintaining structures that allow us to just jump to a specific location, any specific location in any file, right? So direct access is less commonly used. Okay. All right, but files in and of themselves are not what do I want to say? They're not all the same, right? So for that, we have the notion of file types. Name some file types. Okay, a .exe. Yeah. Okay. What else? Okay, text. What was that in the back? Okay, a .doc. Any document file, but the specific document file that we want might be a .doc file or a docx file or an RTF. Is it RTF? Yeah, rich text format file, or anything like, even you might even argue that a PDF is a document file, right? Depending on what you mean by document file, but certainly ODSs, the LibreOffice versions. No, ODP. Yeah. Okay, ODSs are spreadsheets, right? What does that mean? Okay, so the bits are the information, okay? But the bits are also something called the metadata, okay? What does the term metadata mean?
Data about the data.
Yeah, exactly, okay? So you've heard this description before. It's data about data. And what does that mean practically? It means practically that the metadata tells us what the various bits mean or how they should be interpreted. Okay? So like a bitmap, you guys maybe have never even seen this file format before. It used to dominate everything, but the .bmp file type is a lot different than a JPEG, the .jpg file format. Both of those store pictures, okay? But how they store those pictures is very different. And so if you're just handed the data component of a BMP and the data component of a JPEG without some information about who made that and what policies they were following when they made that, what application made this and wrote this file, what policies does this file, what format does this file follow, then you'd be lost trying to interpret just the bits, okay? Even if you knew this was an image, okay, you'd be lost trying to interpret just the bits. If you didn't know it was an image, you might think, oh, this must be a document, or actually you'd have no way of knowing. Maybe it's an executable, right? Because an executable is just a bunch of bits, right? And this is really problematic under those circumstances because executables ought to be treated, right, differently by the OS, right? Certainly with a lot of care by the operating system. You don't want to try and execute a JPEG. That shouldn't be allowed by your operating system, right? So there, at the very least, you can see there needs to be some kind of way to differentiate between executables uh, and pictures. Okay. So how do we do that? But that's just the very least. Obviously, there are other reasons why we'd want to be able to tell, like, whose file is this? Okay. Because when it comes right down to it, when I do this, okay, and then I open my USB, and then I double click on this file, right? The operating system is taking some actions, right? It has identified that I want to open this file with Word, okay? How did it know that? How did it know that? The secret to that is in the metadata that this file is storing, information about the data itself, data about the data, okay? That metadata is stored in a file header. Okay, which is part of the file, but which precedes the actual data that the file encapsulates. And there's a lot of stuff, and we'll talk about some of it. There's a lot of stuff potentially in the file header, right? But one of the things that's in there is something called a magic number. Okay. And the magic number is a short sequence of numbers at the start of the header that identifies the file. Okay. This comes up in areas like digital forensics. Okay. Because your naive attacker might do something like this. Let me take this and I'll rename it and I'll get rid of the .cpp. Okay. Yeah, I'll change it. All right, so now it's just A1 code. Okay. And so if I have a dump or an image of someone's disk, okay, and I'm looking for illicit material. In particular, I'm looking for a piece of code, right? And if I click on this, the Windows at least no longer knows how to open this file, okay? Because I killed the dot blah 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 blah. That's called the file extension, okay? So another way to know what kind of file you have is by carefully naming, I'll go back to it in just a second, carefully naming the file, okay? And making use of the correct file extension, okay? The some number of letters, usually 3 letters, after the file name and after the dot, okay, are the file extension, right? And when I changed this file extension, it used to say a1code.cpp. That was the name of the file. The whole thing was a1code.cpp. When I changed the file to be a1code and dumped the file extension, did you guys notice that Windows warned me not to do that? Okay. It said by changing the file extension, you can change how this file gets treated, right? All right, great. So like if I want to hide a bunch of pictures, okay, that I don't want anyone to see, or documents that I don't want anyone to see, right? Then all I'll do is I'll go in, I'll write a simple program that deletes all of the file extensions, and I'll be safe, right? No, No. If any of you use Unix or Linux, then you'll be aware that it doesn't matter what the file extension is in Linux, okay? In Linux, if I double click on a file like this, having done exactly the same thing to it, it will know that this was a CPP file, okay? Or was a code file or was a text file of some sort. How? Magic numbers. Because the file extension and the magic numbers both try to do the same thing, okay? The file extension attempts to be a way to identify what kind of file this is, right? But it's a less effective, easily changed way to identify what kind of file this is, whereas the file header has this magic number, a sequence of numbers that identifies a particular kind of file or a file format. Who decides on these magic numbers? So if the file format is a standard format, then the standard that defines the file format will also define sort of the standard magic number for that file. So all JPEGs have the same magic number. And I cannot remember what it is, but I bet we can look it up without too much trouble. Yep, FFD8FF is the magic number for all JPEGs. Okay. I don't know. DocX might be more complicated, but let's see if it'll give it to us. Right. So empty archive, and then a different magic number for like different kinds of DocX files. Okay. And these are standard things. Okay. Any kind of file format will have a magic number associated with it. All right. And the magic number associated with it is what some operating systems will do to determine what kind of file it is. All right. Is the use of a magic number, does that strictly tie data to file type? Right? In other words, I said, hey, even the most naive user can come in here and change this file type. In fact, I'll rename this to .jpg. Okay? Notice the emblem beside it changed. Is this a JPEG file? Really? It says it is. The operating system is telling me it is, right? And it's telling me it is because I named it .jpg. When I double click on it, it tries to open it in photos, but like, it's not a picture. That's why it can't interpret the bits, okay, to give me an actual picture. What kind of file is this? Well, it's actually a text file. And if I know that, then I can open this with a text editor. And then all the file is still there, right? So naively, we can fool some operating systems and certainly some users by just changing the file extension. And if I've got a virus, okay, if I've got a virus and I want you to open it up, I'll name it, cutebaby.jpg, okay, and send it to you. And it'll look for all the world like a JPEG file, at least in Windows, because Windows makes the design decision to rely on the file extension. This, in my mind, is a foolish error on the designer of Windows. Okay, Linux and OS X do much better. They look at the magic number. But is the magic number infallible? Everything is made of bits. Okay. Can you change the magic number? Sure. It's not easy. Why is it not easy to do? It's not easy to do because the operating system itself does not provide that functionality. Okay. The operating system itself provides the functionality to rename things, to open files, to delete files, to open them, to edit files, at least through an application, right? but it doesn't provide the opportunity to change the magic number. But all I need to do is download a hex editor, and something like HexEdit, for instance, and there are hundreds of hex editors, will allow me to open up the file and look at the bits themselves grouped into hexadecimal, okay? And so I'll just, if this is a JPEG file, I'll look for the magic number in the header of the JPEG file, right? Yeah, FFD8, FFE0, and then I'll change it, and I'll save the file, okay? I could, or if I could look for an executable, I could change it and save the file. Although, with executables, the operating system needs to be very careful, right? And so generally, there are extra added things that the operating system does to try and keep from running simple viruses that have been named something else, okay? But if you can name a file something.jpg and change its magic number, and then the payload of that file causes the JPEG interpreting application to do something like, oh, I don't know, have a buffer overflow, okay? Then the rest of your file can be used as a buffer overflow attack, right? And then you can run whatever code you want. You can get access, right? So, not to be ignored, often ignored, but really important from the viewpoint of the operating system is all the metadata at the top of that file. All right? Any questions about that?
Is the magic number a variable length?
That is a good question. They should be fixed length, but I don't actually know the answer for sure to that question. Yeah, you're asking an interesting question, like how do you know if all you're doing is looking at hex? How do you know which of these things is the magic number? And that boils down to looking at the specific record, right? So the magic number will be its own record in the metadata. But I don't know if they are fixed length or not. Be a good thing to look up. I'm not sure about that. That's an excellent question. Any other questions? Okay, so let's talk about directories then. The file system is a hierarchical structure. Okay, it is a hierarchy, right? Generally, in the abstraction that we teach to students who are to kids who are and adults, I guess, but to people who are first learning to use programs, is we say, look, directories contain files, and they also, and I'll put the word contain in parentheses, contain other directories. Okay, and so in our file system hierarchy, right, since directories can contain other directories and some files, there must be this is what computer scientists would call a tree, right? And likewise, for all trees, there is a root node, okay? Sort of the top of the tree. I don't know, our trees are upside down in computer science, okay? The root is at the top. So just get used to it, right? But it's the single node that contains, the single directory in this case, that contains all other files and directories, not at one level, but at a series of deeper nested levels, okay, more deeply nested levels, okay? But again, this is really just an abstraction because the truth is that directories are files, okay? They are files that are special files that get treated uniquely by the operating system. And in particular, they are files that contain links to other files and directories. Okay? This is where you need to be comfortable with abstraction. This is why you have to take 255 before you take this class, right? Because we talk about linked lists and we have the notion that things can exist on physical memory in an order that is different from the way we think about how we need to access those things, okay? So the file system is the abstraction that says, okay, I need to double click on this folder, okay, so that I can go into the USB device. Well, wait a second. The USB device, that's this discrete component, okay? That's all that is, right? How can this be part of the computer if I could just remove that computer? Well, because it's been organized as part of this hierarchy, even though it's on a different media entirely, okay? And we don't know how things are laid in to physical memory, okay? In fact, part of the file can be over here, part of the file can be over here, another part can be right here, right? But they're organized into discrete units, okay? And all these files, which are split up and laid in as best as possible, we'll talk about how in just a second, into physical memory, are all linked to in special files called the directory, right? And therefore we have this notion that that directory is full of files, or it contains, quote unquote, contains files, right? When really all it is just a pointers, okay? So pointers to pointers is all we're dealing with. And then when we want to actually open a specific file, okay, we've got to go in and drill down. I don't have anything in here because this computer gets wiped every time. You got to go in and drill down and find the file that we want inside the folders, right? We're just following pointers, okay? And the operating system, because this is a graphical user interface, is providing a graphical cue of what's going on to match the abstraction that we have created. But in fact, behind the scenes, this is just a pointer to this file, which contains a pointer to that file, which contains a pointer to that file, which is a chunk of data that has a certain magic number. And when we click on it or open it, okay, that magic number tells the operating system a bunch of stuff about this file, the metadata tells the operating system a bunch of stuff about this file. But importantly, the magic number says this file is this kind of file. Who do we know that opens this kind of file? What application? Open that application and send this file to them. Okay? But directories are just files that contain lists of other files and other directories, because directories are just files. Okay. Right, so because of that, every file or directory except the root is pointed to by exactly one directory, okay? So if that's the case, then there are multiple ways to access these files. Multiple file paths, if you will. Or to be more precise, there's one file path to every file, But depending on where we are conceptually in the file system, there might be different ways to access a given file. So there's the absolute file path, okay? And then there's the relative file path. Are these terms that you guys are familiar with? I see a little head shaking, a little bit more. Okay, so what's an absolute file path? It contains every step from the root to the file. Okay? So this file, so let's find a file on the C drive. And we'll go to my PC, we'll look at the C drive. All right, so on the C drive, there's a folder called Program Files x86. Inside that, there's one called, just trying to find something interesting. Oh, sure, WinSCP. And inside of that, there's a file called winscp.exe. And that is the executable for WinSCP. So when I double click on it, it runs the executable. Okay. So the absolute file path is something like, and the notation is different depending on what operating system you're using, so that confuses things, but it's something like C:, which is the name of the root folder of my hard drive, /, right? I don't know the sequence we used anymore. What? I guess program files. Okay. / WinSCP / I run out of room, but it's called WinSCP.exe. That's the full absolute file path. Okay. Now let's dial this up. I don't want to use WinSCP. We can. Let's do that again. C drive, program files, WinSCP. Let's go here. Oh man. Am I going to be able to remember my password? Nope. I wonder if I can look it up. Give me just a second. I think I changed it. So bear with me. Nope. That's what I have here. I may have blocked myself out. Well, that was a good idea, but it's not going to work. But you can imagine you've logged into the server before, okay? When you log into the server, you begin your user begins at your specific home folder. Okay, and if you do print working directory from your home folder, you're going to see something like, not / but /. Okay, I don't know, something like home slash whatever your username is. Okay? So the relative file path tells me what the path to the file is from the current directory. Okay? So I can do something like change directory. Okay? Let's say you have a folder called blah, and inside that there's a file called foo.cpp, right? And so I can do like move blah foo.cpp. So that takes me to inside the folder that's in my current directory, look for a file called foo.cpp and move it out of my current directory up another level to some other folder called, test. Okay. And so both of these file paths are relative to the current directory that we're in, to our working directory. Okay. Same idea if you're writing code in C++ and you're using Windows. If you want to do like infile, if infile is an example of an IO object or an OF stream, I think is what it's called, .open. Generally, what I tell my 155 and 255 students is put the file in the directory with the executable. But that's not required, right? If you want to put it in a folder that is inside the same folder the executable is in, then just do \that folder \whatever the file is, or a folder above it \/ whatever. Follow that path. Okay. This is not this alone, that just like this and this will not get you from the root to your file. That's what the absolute file path would do, but it gets you from your current directory to the file. Okay, and therefore, since it's relative to your current directory, it's called the relative file path. All right, does that make sense? You guys got any questions? Yeah.
You were referring to the root as being the root node of each drive. I guess I had a division where
Okay.
the root node would encompass all the drives.
So no. I didn't mean to say that. If I did, I didn't mean to say that. Now, there is a distinction between Windows and Unix. Okay. In Windows, right, each drive has its own sort of file structure. Okay. And so in Windows, what we do is the root folder of the specific device is named differently, okay? According to the scheme that back in the old days, the A drive was the 5 1/4 inch floppy, the B drive was the 3 1/2 inch floppy, and the C drive was the hard drive. And so we still have that where all our C drives are hard drives, okay? Because back when this naming convention took place, hard drives were not often in place, right? Didn't have to have a hard drive. And then like D, E, F, you see like a lot of times E will be your network drives. We don't use network drives here anymore, but when I very first started working here, they still had a network drive up. H is sometimes network drive, but they're named like that. And so you can think of them as not being all under one architecture, under one hierarchy, but being under separate hierarchies. In Linux, and I keep wanting to say like in real operating systems, and I don't mean to insult anyone who's a lover of Windows, but Linux and Unix are like much better operating systems for a lot of reasons, okay? So in my preferred operating system, right, everything is part of the same hierarchy. Root is the root of everything, but that's a logical hierarchy, not a physical one, obviously, right? The logical hierarchy says, look, we're going to put a link somewhere in this hierarchy to the hierarchy that already exists over here, okay? So you append that whole hierarchy in your tree somewhere, okay? Yes, again, an excellent question. Thank you for asking that. Other questions? Okay. All right, so what are the what are the typical contents of a file? I'll just actually show you my notes here. So, typical file attributes include name, data, metadata. Okay, obvious. But also the size of the file. Okay, that's important in case you want to copy the whole thing, right? Because you need to know how much to copy. The type of the file, the location of the file, the protection aspects of the file. However, we're not going to go into the details about protection systems, okay? But every operating system has to have some kind of security which limits which users have access and which applications have access to specific files, okay? Let's just assume those are in place. If you want to know more about that, take the security class. Um, uh, well, there's several of them. Take a security class. Okay. The other thing is use like information about last access, modified time, when created. A lot of that is revealed in like this program, okay, called Windows Explorer, right? Not all of it, obviously, but obviously you've got your file type and your size and your date modified and the name, okay? All right, so here's a design decision then. Where do we keep these file attributes? Okay, the metadata is a specific thing separate from the information about these file attributes. And there's two approaches. I can either keep them all together in the file, or I can keep the file name and perhaps some other critical data and pointers to separate data structure of the attributes, okay? That separate data structure is called the file control block. Now, this is a naming convention that the book likes, yeah, and you've seen process control blocks and like I think there's even a memory control block at some point, something like that. Process control blocks, file control blocks is the same idea, okay? Every file has a file control block. In Unix and Linux, these file control blocks are called inodes. And it's really the inode in that case that the operating system is keeping track of, okay? Because the inode has all those attributes, okay? And the data can or might not be included in the inode depending on how much data there is, okay? But if the data is too big to be stored in the inode itself, then a pointer to where that data is stored in the inode, right, or a series of pointers. Windows does something similar. They don't call their file control blocks inodes. In fact, I can't think of what they call their file control blocks. But they do something similar. And this is the old way of doing it, just keeping all that information together. But as files got bigger, it made things more difficult, and it makes it difficult to search for specific records when we're looking at files. Okay? So here are the operations that we want to be able to do on a file. We need to, as an operating system, provide these operations: create, destroy or delete, open a file, read from a file, write to a file, seek in a file, and close the file. Okay? So when we create a file, the file system, allocates and initializes a new file control block. Allocates a free directory entry continuing the name and pointer to the file control block. Does it have space on the disk yet? No, it doesn't need to outside of where the file control block is being stored. And there's no data. It's just an empty file control block. And to destroy or delete, you simply reverse the allocation of the create, okay? And when you delete a file for non-empty files, the file control block points to a location on the disk, a block on the disk. And we'll talk about disk blocks in just a second. But it points to a location on the disk, and the file system marks the file's disk block as free, okay? And this is another design decision, sort of with security implications. What happens when you delete a file? From the operating system or the file system's point of view, what's actually happening? Do what? Yeah. So you're both right. You're forgetting where the file was, and you're marking down that whatever was here, it's open space now. Okay. When does the data actually in that open space actually get deleted? Yeah, the next time something writes to it, right? So when you delete something, you're not actually getting rid of it. You're just forgetting where it is, okay, as the file system. Now that has security implications, all right? Then open, so we maintain a structure called the open file table to help us with this. It's a data structure that keeps track of all the files that are currently in use. So here are the steps. Verify that the invoking process has the right to access the file and perform the requested operation. Find and allocate a free entry in the open file table. Okay. Allocate read-write buffers as necessary for the given type of file access. Right, and so what that means is just do you have privilege to read? Do you have privilege to write to that specific file? Copy the relevant information from the file control block to the open file table entry, including its file length and location on the disk. Initialize other information, such as the initial position of a sequentially accessed file, and return the index of the allocated open file table entry to the calling process for subsequent access to the file. Okay. Benefits of doing it this way. Minimize the amount of time that we spend reading from the disk. Okay. The open file table has a minuscule amount of space, buffer space, for reading to and writing out to the file. Okay. And so, like, let's take the sequential access technique. In sequential access, effectively when you're, well, let's talk about reading. I'm actually skipping ahead. So in the open file table, we maintain a read-write buffer. So to start, the current position on the file is 0, and the read-write buffer contains the first block of the file. Okay. Just the first chunk of data from the file, right? So disks are organized into blocks. That is a fixed amount that can be read from a disk. That is the amount that can be read from and written out to a disk, the minimum amount. It is the amount that gets read from and written out to, a fixed size amount. So like reading from a disk is an operation that gives us a block of data back. Writing to a disk takes a block of data and writes it out to the disk. Okay. Yeah, so we have a read-write buffer that is effectively, it could be the size of a block, or it could be somewhat smaller than a block. So a general read command will look like this: read IMN, where I is the OFT index, the open file table index. N specifies the number of bytes to read, and M is a location in memory where the data is to be stored. Okay, so the operation read IMN copies the first N bytes from the read-write buffer into M in memory. So the next operation may continue from there. If it reads past the end of the read-write buffer, the file system loads in the next block of the file. Okay? Yeah, so eventually, if you want to read to a specific location in the file, you have to read in all the blocks before that location, right? But the idea is if you're working on a specific part of the file, right, you have the opportunity to read in like a high, an area where you're going to be working, right? You can work within the buffer, not having to read from or write to the disk, and then write that whole thing back out once it's done. Okay, so if that buffer has been modified, then you need to write out the buffer before reading in the next block from the disk. So write then is write IMN, where again, I is the entry in the table, M is the starting location in memory, N is the number of bits to write. And so what the operating system with file system does is it copies N bytes from memory area M into the buffer of the open file, and then the current position and file length are N. So the next write operation starts copying the next N bits from memory to the read-write buffer, but reaches the end of the buffer before all N bytes have been copied. If that happens, then the file system allocates a free disk block and saves the read-write buffer in the new disk block. The operation then copies the remaining bytes from memory to the now empty buffer, starting at offset 0, and the current position and the length change to 2n. Okay. Seek, run through the file using the read-write buffer, close, remove the entry from the open file table. And before you do that, if the read-write buffer needs to be written out, then write out the read-write buffer to the file. Okay. Sounds like a lot, right? It sounds like a lot because it's always been abstracted from you for the most part as users of computers. All right. So how do we allocate disk blocks? Well, again, the disk block is a fixed sequence of bytes on the disk, which can be accessed as a single unit. So the file system views the disk as a sequence of blocks, right? These are concentric circles, really, on the hard drive, okay? Or in a solid state drive, it's less interesting. You just conceptualize it as a long sequence of blocks from the beginning of the disk or drive to the end, okay? And that file may be viewed as a series of one or more blocks, numbered 0 through f-1, where f is the number of blocks containing the file. So the way that disk blocks are allocated to files has a major impact on the efficiency of most file operations, right? A file contains more than one block. It's very, very unusual for a file to be in one block only. Now, there's nobody who enforces how big a block has to be, okay? And they can be different depending on operating system and drive manufacturer, et cetera. But we're assuming that's all been worked out, okay? So the block is a fixed size, right? Files are laid across multiple blocks. How should they be allocated blocks on the disk? One option is to allocate them a continuous chunk of disk space, right? So if the file takes up 5 blocks, you'll know for sure that somewhere on the disk will be 5 blocks, 1, 2, 3, 4, 5, one after another, that all contain that file. Okay? Is that a good idea or a bad idea? Well, it's an idea, and it has its pros and cons. Okay? This is called contiguous block allocation. It is the way things were done in the early days, right? In batch systems, when we didn't have this notion really of multiple usage, okay? Multi-programming. What's wrong with it? Well, what's good about this idea? Having the entire file in contiguous space on the disk. I'm sure it says it up there, but you can use your brain and tell me. What would be good about that?
Pretty easy to find everything.
Okay, it's easy to find everything. All you have to remember is the first block of every file and the size of every file, right? And then it's just a matter of reading that amount of size from the disk. Okay, that's great. Everything is right next to each other. What's bad about this? Well, once you've allocated space for a file, what happens if the file gets bigger? This is analogous, right, to discussions you would have had in 155 and 255 about arrays, right, and storing lists in fixed size arrays, right? Because you tell me you need a new file, and I say, okay, now as the file system, I have to decide how much room are you going to need for this file. Why do I have to decide that right now? Because this file has to be in contiguous space on the disk, which means I have to allocate that amount of space to you, mark it as unavailable, as used, as not free disk space anymore. It's yours. You're that file. How much space should I give you? Don't know, have no way of knowing, can't figure it out, right? I don't want to give you too little, because if I do, then there's no guarantee that there's room on the disk to grow, because there's something right after you probably, okay? Or at least likely. And so you can't grow, no, and I can't put you anywhere else, can't put the other part of you anywhere else, because you've got to be contiguous on disk. If I give you too much space, okay, then what's going to happen? You won't use all that space, and none of the files will use all their space, and so there'll be a lot of fragmentation on the disk, right? Where chunks of disk go unused, so the effective size of the disk is reduced. And I don't know a good way under contiguous block allocation. There's no good way to fix this, okay, because we've designed it poorly. So the answer then is in linked block allocation, where the file control block points to the first block, and each block after that points to the next. It's great. This gives me expandability, okay? If you need more space, I just take the last block, I point to another block that I've allocated to you, and when you jump to that spot on the disk, you'll start to find the rest of your file. And if you run out of space again, you need another block, I'll put a pointer to the last block, point to another place on disk, and you'll start to find the rest of your file. Okay, and we can continue this process hopping around forever. And pointers are internal to the file system, to the file structure itself. But there's the rub. That's a problem because it's wasteful to put pointers to waste space on the disk, keeping track of where the file is, jumping from one to one. And also it makes it difficult to seek in the file because you cannot find a point in the middle of the file, a block in the middle of the file, without sequentially iterating through the entire file to find that block, because the pointer to that location is in the file right before that location. Right? Does that make sense? So for a long time, this was the state of the art, the file allocation table. In fact, this device, my thumb drive, it uses a file allocation table, a FAT32 architecture is what we might call it, file allocation table. Okay? The file allocation table is just an array where each entry corresponds to a disk block. Okay? So you know on your disk how many blocks there are. You have that many entries in your table, in your array. Okay? The file control block points to the first entry in the file allocation table. And if it's just that one block, then you know that's your whole file, right? If it needs another block, it points to the next entry in the file allocation table, identifying another block, right? So we move all the pointers out of the file itself into this file allocation table, which we keep in RAM. Okay? That makes it possible for us to jump to a specific block, okay, in the middle of a file. Now, what's the downside to this? Well, this worked for years. This worked for years. When I was in high school, college, all through the 90s and up into the 2000s, this was the way things were done. Okay, the file allocation table, especially in Windows environments, right? The problem is that disks kept getting bigger. And when you have more disk space, you have more blocks that compose the disk, right? I'm talking orders of magnitude more disk space potentially, especially if you're taking multiple physical disks and treating them as a single virtual disk, okay? Orders of magnitude more blocks, and so you start to have a problem keeping an array with a single list for every possible disk block, okay, in RAM. It becomes huge. It becomes too big to really access effectively. So we introduced indexed allocation. So I should keep an index of blocks for each file in the file control block itself, okay? So the main problem there is, how big should that index be? How much space should I give? Okay, so there's some good research on this that says that your average file is only a couple hundred or only a dozen or so megabytes. Okay, it's not too difficult to take a big computer ecosystem, look at all the files in that ecosystem, all their sizes, and average their size, and it comes out to a dozens, or maybe 100 megabytes. Okay, so you only need a number of blocks large enough to store that big a file on average. What's the problem with that? Are all files average sized or below? No, by definition they can't be, because then that's not what average means, right? If you got huge files, if you got a few huge files, you still need to be able to access those files, okay? So it's not a great solution, right, in and of itself, but Unix has started using expandable index tables. So basically the last entry of the main index table can point to additional index tables, okay, that are not stored as part of the file control block, but are stored as data structures outside the file control block, right? And there's Windows does something similar. It has pointers to a certain number of index tables, which are all null to begin with, but if the file size grows past what can be stored in the index, right, then you begin to point to other indexes. And in fact, the last one can point to indexes of indexes, okay? And so you can actually store in that fashion any number of blocks, addresses of blocks. The downside is that the larger your file is, the slower it is to access that file using this method, okay? Because I have to dereference a bunch of pointers to get to the block, the pointer that points to the block, okay? I don't know, you can't have the best, you can't have all, you can't have everything. It's a balance to strike. Or another way to think about that is, it's still an open area of investigation. All right, any questions about what we've talked about today? So I think that's chapter 8, if memory serves, in your book. And you have your reading, and you're still getting graded on that reading, and it's available on Canvas. Yeah, I'm still formulating what the rest of the semester is going to look like in terms of classes, and I'll let you know when I make a decision. Obviously, after Thanksgiving, we don't have class. There is a possibility to have one more class before Thanksgiving, so I've got to decide about that. And I'll let you know by the next couple of days what that's going to look like. All right. Oh, and your exams, I have not graded them all yet. I'm roughly halfway through, so it's probably a coin flip as to whether I've graded yours or not. And I will try to grade them, the rest of them, by the end of the next couple of days. All right. See you guys later. I'll be in touch.